the electrolysis of water. We take water, H2O, add some electrical energy, and we get hydrogen and oxygen gas. You might be able to tell this is a balanced equation because I think you guys can handle it. Now, what's with this H2 and O2 here? Well, hydrogen and oxygen, just like chlorine, which we saw earlier, are examples of the diatomic elements. You'll never find just an H or an O alone by itself. These elements always pair up and form twos. So that's why we got H2 and O2 here. Now, this equation represents an oxidation reduction process. So electrons are moving, they're being transferred. Let's figure out how they're being transferred by looking at the oxidation numbers. I've got some rules for writing oxidation numbers here. These are just a few of them. These are just the ones that are relevant to the equation that I'm talking about here. Okay, so I've got hydrogen. Hydrogen is +1 when it's with nonmetals like oxygen. Oxygen is usually -2. And then over here, we have hydrogen and oxygen. These are elements by themselves. They're not combined with any other elements. So H2 is going to be 0 and O2 is going to be 0. Okay, so those are the oxidation numbers. And now to see how the electrons are being transferred, let's look at the change in oxidation number. Okay, starting here with hydrogen. Hydrogen is +1, and then over on this side of the equation, it is 0. So its oxidation number is going down, which means that it is undergoing reduction. It is gaining electrons. Oxygen over here is -2, and then on the right side of the equation, it is 0. So oxygen's oxidation number is going up from -2 to 0. Oxidation number going up. That means it is undergoing oxidation, which is loss of electrons. So oxygen is being oxidized. It is losing electrons here. This process is important because just like we saw in the previous example with sodium chloride, this process doesn't happen on its own. It's not spontaneous. You can have water in a glass for hundreds of years if it doesn't evaporate, and it's not going to turn into hydrogen gas and oxygen gas. It's just not going to do that on its own. So just like the previous example, we're going to have to use the electrical energy from a battery to force this process to happen. So now let's take a look at the device that we'd use to do electrolysis of water. It looks a little bit different than the device we talked about earlier because often when we do electrolysis of water, we want to be able to keep or hold on to the oxygen gas and the hydrogen gas that get produced. So this is the electrolytic cell that we'd use to do the electrolysis of water. Here's what's going on. We have a container that has water in it. And then we got these weird looking things here. What are these? Well, these are actually test tubes that are filled with water and are put upside down in the top of this container. So it's like you'd fill them with water and then you'd very carefully turn them upside down so they're still filled with water and they're in the container. Then just like in the previous example, we've got these electrodes here. The electrodes are in the test tubes. You can see that they're like sticking in the test tubes, and the electrodes are hooked up to the battery. It's the electrodes that are putting electrons into the water or pulling electrons out of the water. Okay? And then finally, of course, we have the water. Now I should say this electrolysis process doesn't just happen in distilled pure water. We got to add a little something like sulfuric acid here to allow electricity to flow through the water. So you can't just do this in pure water. Got to add what we call an electrolyte like H2SO4 sulfuric acid. Okay, now let's look at how these electrodes here are connected to the battery. Okay, this electrode here is hooked up to the negative side of the battery. So electrons, as you can see here, are moving out of the negative side and they're being pushed into this electrode. So that means that this is the cathode. It's the site of reduction. Over here, this electrode is hooked up to the positive side of the battery. So electrons are moving out of it. That means that oxidation is going to be taking place. It's going to be pulling electrons from things. and this is what we call the anode. So we've got hydrogen gas and oxygen gas. What gets made where? Well, hydrogen here in water gets reduced to form hydrogen gas. So the cathode, the site of reduction, is going to be where hydrogen gas gets produced, H2 produced here at the cathode. And then oxygen in water gets oxidized to form oxygen gas. So over here at the anode, the site of oxidation, oxygen is going to be produced. So we hook everything together, we add a little sulfuric acid to the water, connect the electrodes to the battery, and we'll start seeing bubbles. That's the gas being formed on the electrodes. And those bubbles are going to start moving up to the top of the test tubes. And if you look carefully, you see a really cool thing happen. The level of the water starts to go down because gas is flowing up, it's floating up, and it's collecting at the top of the test tubes, and it's forcing the water down. So you see the water level slowly move down as the gas collects at the top of the test tubes. It's really cool, and you can watch this, you can see this happen in the lab. Now, something else really interesting happens. You'll see what I did here, and I'm not just being careless. On the side that's producing hydrogen, you get twice as much gas as the side that's producing oxygen. There's twice as much hydrogen gas as oxygen gas. Why is that? Well, take a look at this balanced equation here, okay? We have 2 H2 and just 1 O2. So there is a 2-to-1 ratio of hydrogen gas to oxygen gas. So that means that when we do this electrolysis, we are physically going to get twice as much hydrogen gas in this test tube as we get oxygen gas over here. Okay, so that's the big picture of how we do electrolysis in the lab and what's going on here in the electrolytic cell. Now let's take a look at the half reactions for the reduction of hydrogen and the oxidation of oxygen. Let's break this process down into the two half reactions that make it up. Now let me just tell you, when it comes to writing half reactions for the electrolysis of water, there are so many different ways to do it. And it seems like every textbook or every teacher has their own way of writing these half reactions. In this video, I'm using the half reactions that I think make most sense. But if your teacher or textbook has a way they really want you to do it instead, just learn their method. Every way of writing these is essentially equivalent. They're essentially the same. They just look a little bit different. So again, I'm using the reactions that I think make most sense for this video. Let's start with a reduction of hydrogen. I really want to show you what's going on with the atoms and electrons in these half reactions. Okay, so we start with 2 molecules of water, H2O, and you'll see that I've written the oxidation numbers above each of the atoms. So in the reduction of hydrogen, essentially what happens is it's like we take 1 hydrogen from each of these water molecules and pull them off, and then we combine them to make a molecule of H2, hydrogen gas. Now what has to happen with the electrons for this to take place? Well, each of the hydrogens over here has an oxidation number of +1, but then they have an oxidation number of 0 over here. So that means that each of these hydrogens has to gain 1 electron so that its oxidation number can be bumped up by 1. Okay, here's a diagram sort of showing what's happening here. Okay, this hydrogen was +1 and then it gains an electron and becomes 0. This hydrogen was +1 and it gained an electron and became 0. Where do these electrons come from in the electrolytic cell? Well, they came from the cathode, because the cathode is what pushes out electrons. The cathode is where reduction happens. Okay, so we get 1 molecule of H2, but then we have these parts of the water molecule which are just left behind. So we get an O and an H. And these two things together have a negative charge of 1-. These are polyatomic ions, are called a hydroxide ion. And the reason why they have a charge here is because notice that their oxidation numbers haven't changed, because we're not adding or removing electrons from the rest of the water molecule. So these numbers are just staying the same as they were over here. You add these oxidation numbers up and you get -1, -1. So that's the charge of this ion. Okay, so this is how the reduction happens with pictures. Let's look at how we can actually write an equation, actual half reaction for what's going on here. We start with 2 molecules of H2O, and then we gain 2 electrons, so plus 2E minus, and that gives us 1 molecule of H2, and then we get 2 OH minuses. So that's the half reaction here. That's a half reaction for the reduction of hydrogen. Now let's take a look at the half reaction for the oxidation of oxygen, okay? Just like up here, we start with 2 molecules of H2O. And for the oxidation of oxygen, it's going to be like we pull off these 2 oxygen atoms to make a molecule of O2 oxygen gas. Now, how about the electrons in this case? Well, both of these oxygens were -2 for their oxidation number over here, and then they became 0 over here. So each one of them has to lose 2 electrons to become 0. This one was -2, then it loses 2 electrons, becomes 0. This one was -2, it lost 2 electrons to bump its oxidation number up. It's losing electrons to 0. So that's what's going on here. Now, where are these electrons going? Well, the electrons are going to the anode, because it's the anode in oxidation reduction reactions that is pulling in electrons. Okay, so this is what's happening with the oxygen. What about the rest of this? Well, we have 4 hydrogens left over after we pull off those oxygens, and their oxidation numbers are not changing because we're not adding or removing electrons. So we're just going to get 4 H pluses over here left over that have an oxidation number of +1 because that's not changing. Let's do the same thing that we did up here. Let's write a half reaction for the process. This is a little bit more challenging. As before, I'm going to write it incorrectly first, and then we're going to fix it. Okay, so we start with 2 H2O, and then we lose 4 electrons. -2, -2, so -4 electrons. And that gives us O2 plus 4 H plus, these up here. Now, as you probably know, we can't use the subtraction sign in a chemical equation, so we have to make this 4 electrons and put it over here. So this is what we're going to get instead. We just move this 4 electrons over here, 4E minus, and there we go. Okay, there we go. Now we can see it. And these are the half reactions for the reduction of hydrogen and the oxidation of oxygen. Now let's combine them, put them together. Okay, now so for combining these half reactions, we want them to have the same number of electrons. The reduction half reaction that only has 2 electrons, we have 4 here. So the way we're going to solve this is we're going to take this whole equation and we're going to multiply it by 2. And distributing this 2 across the equation, we are going to end up with this: 4H2O, 4 electrons, 2H2, and 4 OH minus. So that is our new reduction half reaction. Now we can take these 2 half reactions and add them together. We're going to get this. We take everything from this side of the equation and put it here: 4H2O, 4E minus, 2H2O. Then we have our arrow, and then we have 2H2, 4OH minus, O2 plus 4H plus 4E minus. All right, now there are a few things that we can do here. If something appears on both sides of the arrow here, we can cancel it out. Okay, so we'll get rid of this one and we'll get rid of this one. But that's not all we can do. Look at this. We have 4OH minus here and we have 4H plus. OH minus and H plus combine to make water. Now also, look at this. We have 4H2O here and 2H2O here. So we can combine these to get 6H2O. All right? So here's how we can rewrite it. We pull these together and get 6H2O. We get rid of the electrons there, and then we have 2H2. We combine 4OH minus and 4H plus to get 4H2O, and then we have our oxygen. But you know what, there's actually one more thing we can do, because look, we have H2O on both sides of the equation. So I can subtract it so we can get rid of it from one side. I'm going to do minus 4H2O here. I'm going to do minus 4H2O here. That's completely going to get rid of the H2O on this side, and it's going to leave me with 6 minus 4, 2H2O on this side. Here is the same balanced equation that we used when we started. You put the half reactions together, and this is what you get. So that is the electrolysis of water. Hydrogen is reduced, it gains electrons, this happens at the cathode, the site of reduction, and H2 is produced there. Then oxygen is oxidized, it loses electrons, this happens at the anode, the site of oxidation, where the oxygen is produced. We got these two electrodes in these upside down test tubes, and the gas, the hydrogen and oxygen, collects at the top. And we've seen that we get twice as much hydrogen gas as oxygen. And that's just because in our balanced chemical equation, there's a ratio of 2 hydrogens to 1 oxygen. So that is why we get twice as much hydrogen here as oxygen here. So that's how electrolysis works. That's how you put electrical energy into a chemical reaction to make something happen that wouldn't happen otherwise. Something like taking sodium chloride and breaking it apart into sodium metal and chlorine gas, or something like taking water and splitting it apart into hydrogen gas and oxygen gas.